This lecture video is about graphing logarithmic functions. So we've looked at log functions a little bit already and how to solve them and how to go back and forth between the log function and the exponential. And so in our first example here, we're going to graph y equals log base 2 of x and y equals 2 raised to the x power. So first I want to graph actually this exponential function, so we'll do that in red. And so we'll just make up a table. We've graphed these before. And you need the 3 points, -1, 0, and 1. And when x is -1, then we would get 2 to the negative first, which is 1/2. And then when x is 0, we get 2 to the 0, which is 1. And 2 to the first, which is going to be 2. So we have the 3 points, -1, 1/2. And 0, 1, and then 1, 2. And remember, these get really close to this x-axis but never cross it, and then they get fairly large fairly fast. So here's a graph of y equals 2 to the x. And now in blue, we'll graph y equals log base 2 of x. And so I find that graphing log functions is easier if you rewrite it in exponential form. So if we rewrite this in exponential form, then what do we get? Well, we get 2 raised to the y is equal to x. And we're going to plot some points just like we have done before. And now since we're raising 2 to the y power, it would be easiest if we picked y's instead of x's, because it's easier for me to say, well, I want to raise 2 to, the negative first, the 0, and the first power, than it is to say, well, to list powers of x, I guess, is how you'd think about that. So I'm going to pick my y's. I want my y's to be -1, 0, and 1. And so then the x values are going to be 2 raised to the y, so that's 2 to the negative first, that gives me 1/2. And 2 to the 0 will give us 1, and then 2 to the first gives us 2. So now for our log function, log base 2 of x, we have these points. So 1/2, -1. So here's x equals 1/2, and then y is -1. And then we have 1, 0. And then we have 2, 1. And so the log functions get really close to the y-axis, but never really cross it. And then they go off to positive infinity this way. Okay, so now if I draw in as a dashed line the line y equals x, you'll see that these two are reflections across this line y equals x from one another. And so this y equals log base 2 of x is the inverse function for y equals 2 to the x. So these two functions are inverses of one another. Okay, and I'm just going to label my points here. So I had 2, 1, and this was 1, 0, and 1/2, -1. And here I had 1/2, -1, 1/2, and then 0, 1, and 1, 2. So the other thing that I wanted you to notice about this is our points that we had on our graph. So the exponential function had the point 1, 2. Our log function had the point 2, 1. So they're opposite of each other. The points are flip-flopped. And then we had 0, 1 on the exponential and the point 1, 0 on the log. We had -1, 1/2 on the exponential and 1/2, -1 on the log. So just want you to be aware of that. So there are 3 points that you should graph all the time. If you have y equals b raised to the x, and it's exactly in this form, so you don't have plus or minus any number anywhere up in the exponent or down below. Then there are 3 points that you should plot each time, and the first one is -1, 1 over b, and then 0, 1, and the third one is 1b. So those are the 3 points for a exponential graph that has exactly this form that you should plot. If you have a log function, so y equals log base b of x, then you should graph flip-flopping all of these are the 3 points that you would plot. So maybe I should try to see where I can put this. This I'm going to erase, and we'll put them right here. You would want to plot the following. So it would be 1 over b -1, and 1, 0, and b, 1. Okay? So if you have the log function, you have these 3 points. If you have the exponential function, you have these 3 points always. Okay, our next example is y equals log base 2 of x plus 1. And so this plus 1, it's not inside with the x, it's being added to the y value, and so this is moving our graph up 1 unit. And so basically what you would do then is add 1 to each y value. And that way you could just use these 3 base points that we have here, only add 1 to each of these y values, and then these values would stay the same. So let's look at our normal log base 2 function that we just graphed. And so what we want is we want to add 1 to this, which means that we're going to be shifting this up 1 unit. So we're instead of we'll put this in a different color. So this point will get shifted up 1 unit. This point will get shifted up 1 unit, and also this point will get shifted up 1 unit. Okay, so there's our new points. And our original graph had the points. Remember, we picked our y values, -1, 0, and 1, and they were the x values then were 1/2, 1, and 2. This was for, we rewrote it as an exponential, remember, 2 to the y is equal to x. And so all we want to do is add 1 to each of these values. These x values didn't change because we're just shifting them up 1 unit each. And so you would just add 1 to each of these values. And so our new y value would be 2 here, 1 here, and 0 there. So our points are 1/2, 0, and 1, 1, and 2, 2. And so again, these curve around, it gets really close to the y-axis, but it never actually crosses it. This black one gets really close to the y-axis also and never crosses it. So this would be y equals log base 2 of x plus 1. So it's just this graph shifted up 1 unit. Oops, we need to go hit the graphs up over here first. So our next one is y equals log base 2 of x, and but then now it's minus 2. So what this minus 2 is doing to your graph is it's shifting it down 2. And so you can start with your base points. That's what I would always do anyways. So the base points, when you had y equals log base 2 of x, remember this was when we picked our y values, because this is the same as 2 to the y equals x. And so we picked y to be -1, 0, and 1, and the corresponding x values were 1/2, 1, and 2. And so again, what this minus 2 is doing is shifting your graph down 2 units. So if you shift a number down, or a graph down 2 units, you're going to be subtracting 2 from all the y values. So you would want to, I'll put that back in red. So we're going to want to subtract 2 from each of these. And -1 minus 2 is -3, and 0 minus 2 is -2, and 1 minus 2 is -1. So we'll have the points 1/2, -3, oops, and 1, -2. Oops, that's not 1, -2. Oh, yes, it is. And then our last point is 2, -1. And so again, this is curving around, gets very close to this y-axis, but never actually crosses it. So this is the graph for y equals log base 2 of x minus 2. And should label our points on here. We have the point 1/2, -3, 1, -2, and 2, -1. And the domain for this log function then, there isn't going to be anything less than 0, and it can't ever equal 0. The x values can't. And the x values go off to positive infinity. So the farthest left you would ever go is to 0, not including 0, and it goes off to positive infinity. And then the range, remember the range of the y values, so this goes down forever, so negative infinity. And then it also goes up forever, because this very slowly goes up forever. So the range would be positive infinity. Okay, our next example, y equals log base 3 of x minus 1. So this time, this minus 1 is inside next to the x, and so this is shifting right or left. Remember, this does opposite of what you normally think, so a minus 1 means we're going to go right 1. And so set up your table. We want x and y. And so we would pick our y's, because we would rewrite this as 3 raised to the y is equal to x minus 1. And so it's just easier to pick the y values. So in the basic graph, because the base is 3, this -1 would give us 1/3, 0 would give us 1, and 1 would give us 3. Remember, it's 1 over the base, 1 and the base. So that's what we would have. This is shifting the graph to the right 1 unit, so we're going to go right 1. So that means that instead of not crossing the y-axis, we're not going to cross the vertical line x equals 1. And right 1 means that you're shifting to the right, so that means we would add 1 to each of our x values. So you're going to want to add 1 to each of these. So 1/3 plus 1, and 1 plus 1, and 3 plus 1 would be our new points, our new x values. So that would be 1 and 1/3. And you can just leave it as a mixed number if you want. So those are our x values, and the y values would still be -1, 0, and 1. So we have 1 1/3, and -1 is 1 point. And then we have the point 2, 0, and then we have the point 4, 1. So again, the graph is curving towards this asymptote, which is the line x equals 1. And labeling our points, we have 1 1/3, -1, and we have the point 2, 0, and 4, 1. And our domain and range domain here is going to be from 1 to infinity, and the range negative infinity to positive infinity. Okay, so it goes down forever, and it will eventually go up forever, but it goes up very slowly. And again, this will never cross this line x equals 1, so the smallest x value is something close to 1, but not equal to 1, so we use a round bracket with 1, and then it goes on to the right forever, so off to positive infinity. And just a couple more of these graphs. So we have y equals log base 3 of x plus 4. So this plus 4, remember, it does opposite what it says it's going to do because it's inside next to the x. So that means we're going to go left 4. So left 4 means that we want to subtract 4 from all of the x coordinates. So the basic xy coordinates for this graph, again, the y values are going to be negative 1, 0, and 1, and the normal x values would be, so we have log base 3, so it would be 1/3, 1, and 3. We're subtracting 4 from each of these. So 1/3 minus 4, so that 1/3 is the same as, or 4 is the same as 12/3. So 1/3 minus 12/3 would give us negative 11/3, which is negative 3 2/3. Can't really read that very well, but, and then 1 minus 4 would be negative 3, and 3 minus 4 would be negative 1. So we have the point negative 3 2/3, negative 1. And our next point is negative 3, 0. And the next point is negative 1, 1. And so this is shifting our asymptote to the left 4. So we would have a dashed line going down at negative 4, or x equals negative 4. And so this graph, again, is going to curve very close to this line x equals negative 4, but never actually cross it. So our domain, negative 4 with a round bracket, and it goes on to the right forever. And the range, it goes down forever, so that means negative infinity, and it goes up very slowly forever, so that means positive infinity for the range. And our last one, y equals negative log base 2 of x. So this negative sign means that we're going to change all of the y values from positive to negative or negative to positive. So that means that we're flipping over the x-axis. Is what that's going to do to our graph. And so this log has a base of 2. So the points that we would have would be negative 1, 0, 1, and this would be 1/2, 1, and 2. And what this is doing is flipping it over the x-axis, so we're really multiplying all of these by negative 1. And so we would have, the new point would be 1, 0, and negative 1. So we have the point 1/2, 1. And we have the point 1, 0. And we have the point 2, negative 1. So instead of, so let's scroll back to a regular log function here. So the very first one that we did, or one of the first ones. So the graph gets really, really close to the y-axis from down below. But if we flip this over the x-axis, see, instead of going down, it would be going up then and getting close to that y-axis. So that's what this graph is doing. So it's curving around and getting very, very close to the y-axis, never actually crossing it, and it's going off to the right forever. Whoops, I can't draw the curve in that way. There, that's a little bit better. And let me get those points filled in. So we have the points 1/2, 1, and 1, 0, and a 2, -1. And the domain. So this flipping didn't change our domain. It still can't go beyond 0. So 0 to positive infinity. And then the range. So this does go down forever. It goes down very slowly, but it does in fact go down forever, and it obviously goes up forever. So the range would be from -infinity to infinity. And that is the last example on graphing log functions. So if you have any questions, let me know. Thanks.